understanding of force systems and building up to the goals that we know we're aiming towards based on what we did early on in the course there, and seeing the example machine problem. So we're going to move on into Chapter 2. And Chapter 2 continues this development, kind of focuses on just a couple of key things in 2. The first one being just a kind of a first jab, if you will, at equilibrium. And we're going to take a look at a problem that touches on that touches on equilibrium. So we're going to get that. And then we're going to move on into the definition of moments. And as I've told you all before, and I sincerely mean it when I say things like this, I'm always going to tell you when stuff is really important, and I'll tell you when stuff's not so important. And trust me, this stuff I'm about to show you today on moments, this is really, really important stuff. So I want to make sure that we understand that, understand the significance as we go forward. And I'll also remind you too, just to remember that right now we're limiting ourselves in our conversations, we're limiting ourselves to 2D force systems, which again, if you're going to take some time, I encourage you to do so. Take some time to go through Chapter 2 in your book. Skip your sections involving 3D. There's nothing there that we need to dig into right away. But when it does come to, and again, spending any time in Chapter 2, I want to be crystal clear when I say this. As I said to everybody at the very beginning of the course, the job at hand for all of us in the very few weeks that we really have together for this course is to really get good at some fundamentals, and then the details will come in time. I want to make sure that you all understand that doesn't mean that we shouldn't be looking at the details. It means we don't need to understand them, we don't need to make them part of everything we do. But if you're going to spend some time going through Chapter 2, I just want to encourage you to not only look for the things that we're covering in class, because those are the fundamentals, obviously, but the depth of knowledge that you get by reading about some of the details, some of the little things that we're not going to cover, because once again, we can't possibly cover everything. So understand that when I suggest going through the chapters and reading through, what I'm really saying is spend that time, invest that time in yourself to get at least some exposure to those details so you can see how they dovetail with what we're doing with the fundamentals that we're covering here in class. And I don't know if I've said this to you all yet in this class, but you will hear me say this a few times before this course is over with. I want you to always remember something. Of all the teachers and all the professors you're ever going to have in your life, the best one you'll ever have is you. So learning how to learn from what you read, knowledge you can gain from something like reading a chapter, you just can't beat that, folks. So remember, you're the best professor you're ever going to have. Become that. Let's start things off this morning with a problem. This is a problem that is provided to us in Chapter 2 of at least some of the later versions of the book. Drawn it up here on the board. As you guys know, I always trust that the drawing in the book itself is it's going to be a lot better than anything I'll ever draw. But I think this kind of gets the point across. We've got ourselves a tower here. You can imagine this is like a cell tower, or some sort of a communications tower out there somewhere in the world. And note first up, before we get deeper into this, that all dimensions that you provide here are in meters. So instead of just writing M behind everything, I like to keep things a little uncluttered. Just know that every one of those dimensions are in meters. Here's what's going on here, folks. I want to read the narrative from the book, the narrative for this particular problem for you. And before I read the narrative, there's another thing that I want to talk about when it comes to problem solving. And it starts with what we're doing right now. Most every problem that we're going to come across in this class is a story problem. We've all dealt with those many, many times. And trust me when I say, if statics that you're in right now, if this is one of your first pure engineering courses, then get used to this format. We're going to see a lot of these things over the next several years. These problems will always present as a narrative. I'm about to read the narrative. In other words, that's the story of the story problem. Usually, there will be a graphic image that's going to come with it. But the bad news is a lot of times you don't get a graphic to go along with it, which means you have to develop the skill set, the knack, to convert a narrative problem into a graphic format, because a picture's worth how many words all? 1,000 words, right? So you can go on and drone on and on about what's going on in the narrative, but at the end of the day, you gotta have some sort of a graphic image. The reason I'm emphasizing this is all the problems that we're going to work here And in setting you up for what you're going to do for the next several years, you want to get into this basic approach, this habit of this basic approach, and that is this. Whenever we're encountering a problem, start with the narrative. Read the narrative, understand what the narrative is telling us, and then use that to either understand a graphic image that's been given to you, or if you need to, create your own graphic image. There's a sequence here. Start with the narrative, create a graphic. The graphic becomes the visual model for us, and as we're going to see here in statics, those two important foundational steps, we're going to convert those then into the models from which the math will come from which we'll solve the problem. Now, we've already seen that. Think about this. We saw that in the can crusher, right? We were already given a graphic image, but what if we weren't? What if you were just given a paragraph and somebody says, hey, I need you to create some sort of a single-handled tool that when pulled up with 20 pounds of force, it's going to crush a can. No image. All right, fine. Then you've started with the narrative. From that, you've got to create a graphic of what you have in mind, your idea of how this is going to get done. Now, keep in mind, what we saw a couple of days ago was that part was already done for us, right? But did you notice how from that picture, it was from that picture that we pulled information out to create the free body diagrams. Those are the models from which the math comes from to solve the problem. So this sequence that I'm talking about this morning, narrative, graphic, and then the model from which the math will come to solve the problem. That three-step process is ubiquitous, not only in what we do here, but we're going to see it over and over in later courses, solids, dynamic systems, heat transfer, whatever. You're going to see that over and over again, so you want to get good at that. Meaning this. As we start by reading the narrative of this problem, reading is one thing. Finding the key bits of information is the thing. Okay? In other words, there might be a bunch of fluff in the words, but we want to find the things that matter. What are the little keywords? What are the little buzzwords that help us understand how to think about this? We're going to see this as we go through it. I'll emphasize them as we go here. So it goes like this. Referring again to that picture right there. Let me get out of the way so y'all can see it. The guide cables AB and AC. So we're talking about these two cables right here. I'm 4 words into it and I've stopped. AC, AB. All right, we're talking about the so-called guide cables. The guide cables AB, AC are attached to the top of the transmission tower. Now, hear this word I'm about to emphasize. The tension in cable AB is 8 kilonewtons. Tension. Very important idea here, folks. Cables are among the few things that we're going to look at here in statics that are not rigid body elements. All right? Take this tabletop right here, for example. We view the tabletop as a rigid body. I can't compress it. I can't extend it. I can't fold it, I can't make it smile at me, it's a rigid body. On the other hand, if I had a cable attached to the table, or a chain, or a belt, something like that. Yeah, questions?
Is that 8 kilonewtons?
Yeah, 8 kilonewtons, yep, 8 kilonewtons. If I had a cable, so imagine this, I got a chunk of rope in my hand right here. I'm going to attach the rope through this hole in this table right here. Now, y'all know, this is all about imparting forces onto mechanical systems. So, one end of my rope is tied into that hole in that table right there. I'm holding the other end right now, and I want to use this rope to impart a force on the table that's going that way. Can I do it? Nope. Why? Not a rigid body. So if I really had a rope here, I'm holding it, you can imagine the rope's kind of, let's say it's not a whole lot of slack in the rope right here, kind of holding it tight, and I want to use this to push the table that way. All that's going to happen is if I move the rope this way, the rope's just going to do this, and the table does what? Nothing, right? Well, if we want to formalize that idea, what that means is I can't use a non-rigid member to apply a compressive force. I took my same rope right here. I want to compress the table. I want to squeeze it together. I can't take my rope and push down on it and squeeze the table together. No can do. On the other hand, that same rope tied in here, if I want to impart a force that's going to go this way towards that wall over there with my rope, now I can do that
Why? Because in the non-rigid member, I can impart tension forces. If I had an open hand here and I pull on that like there, I face resistance, right? I face resistance to motion. On the other hand, if I do this, I face no resistance, or effectively no resistance to motion. No compressive forces, but yes, tension forces. So what we just saw right there in the wording of this narrative, when it said, again, the tension in cable AB is 8 kilonewtons, that is telling us that we're going to treat the cable as a non-rigid body that can only impart tensile tension forces. It can't compress, but it can pull. So the tension in cable AB is 8 kilonewtons. The ask in the narrative goes like this: determine the required tension T in cable AC. So we know what's going on here. We're going to figure out how much tension force do we need to put in that cable, such that the net effect of the two cable tensions, the net effect meaning combined effect of the two cable tensions, is a downward force at point A. And then we're asked to determine the resultant, the magnitude actually, resultant of that downward force. So let's break this up and make sure that we're crystal clear, because once again, this part that I'm doing right now may seem trivial, it's critical. We're taking the narrative, we want to understand what we're being asked to do. We know that there's an 8 kilonewton tension in this cable over here. We want to figure out how much tension we're going to get over here so that, I want to read these words one more time, so that the, quote, the net effect, the total effect of the two cable tensions is a downward force at point A. What's implied in that is if the net effect is a downward force here, that means there is no horizontal force. If we think about the standard X-Y axis, what we're really saying is we want to put a tension in that cable, in cable AC, so that that tension creates nothing but a Y direction force and, by extension, no X direction force. See, that's the key to understanding this problem. That's the key to solving this problem. So, okay, how do we do that? Well, if the game is figuring out what that unknown tension is, again, think about our model. We're going to read the narrative. If we don't already have a graphic, we're going to create a graphic, but we've got a graphic, so step 1, step 2, done. But now we need to create a model. This also is going to be a visual model that we're going to use to create the math to solve the problem. For us, it's a free body diagram. Now, we haven't formalized any education yet in free body diagrams, but we've already seen how that's done. We pick something, we sketch that something, and then we apply forces. If there are any applied forces, none. I should say we draw in forces. If there are any applied forces, we put those there. If there's a weight, we put that there. And then we also include forces for where we used to be in contact with something. We put that there too. So now we go to, all right, we're gonna make a free body diagram of something over here. Got it. Was there any limitation from what we talked about before? Was there any limitation at all on what you could do a free body diagram of? Like, yeah, you can do it on these things, but you can't do it on that. There wasn't any. There is absolutely nothing that we can't make a free body diagram of. Absolutely nothing. So take, for example, let's say that I want to do a free body diagram of just a chunk of cable AB. Now, this is not to solve the problem, let's make a point. I want to do a free body diagram of a chunk of cable AB. Like, let's say I want to take that chunk right there. Step 1, draw the thing. There's my chunk of cable AB. We already know that cable AB, according to the narrative of the problem, the cable AB has 8 kilonewtons of force, but we were told that that was a tension force, right? It's a tension force. Now, as we talked about before, when we're drawing free body diagrams, when we don't know the directionality of a force, we don't need to know its direction because the math will tell us what it is, right? But this is a different scenario. In this case, we know the direction because we're told it is a tension force, meaning the force here in this cable is trying to pull this cable apart. It's not trying to compress it. So therefore, the 8 kilonewtons of force which is going to be collinear with the cable itself. This is another aspect of non-rigid bodies like cables and chains and wires and stuff like that. The force will always go along the line of action of the element itself, provided that gravity isn't acting upon it, and we'll talk about that in chapter 3. But for now, we know that the forces in this are an 8 kilonewton force going that way. And remember, Newton's law, equal and opposite, so opposite direction down here. 8 kilonewtons going like so. That's the free body diagram of that chunk of cable AC. I'm sorry, AB. So now, folks, with that, let's go back. We still want to solve the problem, right? So in this case here, we're going to draw a free body diagram of something that's going to allow us to solve this problem. There's a couple of possibilities, a couple of great possibilities. One, maybe I could draw a free body diagram with just this cable and just this cable connected together, cut them, and draw my forces associated with the cable on that. Would that solve the problem? The answer, by the way, is yeah, that'd do it. But there's even an easier play here yet. If I can draw a free body diagram of anything, then why can't I just draw a free body diagram with the place where these two things are connected together, right? So in that case, my free body diagram is going to have the profoundly complicated artwork of here's where the two cables come together, like that. Now, some might say, well, but isn't that attached to the tower? It is attached to the tower, but that's an attachment going in the Z direction, so we don't know anything about that because our world is 2D right now, right? We're not worried about that. But we do know this, coming off of this place where these two cables are connecting together, I have the force in this cable here, and I can draw that force in that cable going downward like so. In fact, I know that this is going to be 8 kilonewtons because I've already been told it's 8 kilonewtons. And why did I draw that arrow down that way? Because, again, equal and opposite. If the cable is in tension and its force here, which ostensibly we could imagine that this is the place where it's connected to that dot over there, if the force in the cable is going that way, then according to Newton's law, the reaction force has got to be going in the equal and opposite sense. So we did that. Now, cable AC, we don't know the tension in it, right? But we also know that it's in tension. So therefore, we can draw this force that's going off like so. And let's call that something. Let's call it TAC maybe for the tension in cable AC. And again, there's no limitation. Call it whatever you want. If you want to just call it AC, perfectly fine. If you want to call it my dog Spot, who cares? Just give it a name. So now, with that, and again, put this into perspective of how we are solving the problem. Narrative, graphic, now a model from which the math can come from. And in this model, let's not forget, we want to draw an axis system. So how about we do our axis system like this? There's our x-axis, and let's let our y-axis go like that. Does it matter that I drew it that way, folks? Does it make one iota of difference that I drew my axis system like that? No, not one bit. I could have just as easily just came over here and did something like this and been just as happy with it and got the same result. But for reasons that will become apparent here in a second, I threw that in right there because the next thing I need to understand is I'm going to need some kind of directionality. We talked about that the other day. Remember, if I want to be able to specify a force, which is a vector quantity, I need to know how much, direction, and point of application. In this case right here, the how much are these things, point of application here, and then the direction for a two-dimensional force system, we need one angle, right? So I need to get an angle. Make sure I draw this thing, okay? I need to get an angle between the x-axis and this force here. I'm gonna call this angle beta. You get an angle between the x-axis and this force over here, and I'll call that force alpha. And then again, once again, I can call them whatever the heck I want to. So now I need those angles. If I get those angles, then I've got this thing figured out. To get them, now we're back to our original diagram, the original graphic image of the problem at hand. And remember, we've talked about this before, folks. We look for triangles, right? So for example, if I want to figure out what angle alpha is over there, I see a triangle right here that I can create, which involves a leg going up like this, a leg going over like this, and here's my angle alpha. Now, let me
presume that that is a right triangle. If we look at it, we've got dimensions given to us. So this dimension from here to here is 40, which means this leg of this triangle here happens to also be 40. This dimension from here up to here must be the combination of this 20 plus this 30, so I got a 50 over here. And therefore, if you look at it right now, I know, with respect to the way I define angle alpha, I know the opposite leg of the triangle, I know the adjacent leg of the triangle, and opposite and adjacent, that's tangent, right? So therefore, the tangent of alpha would be, again, opposite over adjacent, and that would be, in this case, 50 divided by 40, which means that alpha, therefore, would be the inverse tangent of 50 over 40, or 1.25. And folks, if we plug that in and crank that all out, we're going to find out that alpha ends up being 51.34 degrees. And then we got beta to deal with. Now, same thing, look for triangles, right? So in this case here, easy to see, you've got a triangle right here, going down to here. We know this leg of this triangle is going to be 30. We know that this leg over here is going to be 50. We know here's our beta angle here. So in this case here, got opposite, got adjacent. So the tangent of beta, which again is opposite over adjacent, that's going to be equal to 30 divided by 50, or 0.6, and therefore beta is the inverse tangent of 0.6. And folks, when you plug that in and crank that out, you're going to find out that beta ends up being about 30.96 degrees. So now with that, I've got more information that I can add to my my diagram that I'm using to get my math. Remember, we've talked about this too. Whenever you know something, whenever you know the value of something, make sure that shows up on your model. Anything short of that means you're adding an unknown that is not still really an unknown. So right now I know that this is 30.96 degrees. And I know my alpha over here is 51.34 degrees. And we are in great shape. Now, folks, you all know too, as we're going through this, if there's anything that's not crystal clear or that I'm overlooking, don't hesitate. Shout it all out. I assume, since I'm not hearing anything, that everybody's good at the moment, but again, if you got any questions, fire away. So now where do we go? Well, we've already seen the end. We know that this is all about equations of equilibrium. Suming forces in the x direction, suming forces in the y direction, right? The other day, and even before that, even when we were working the problem with the can crusher, we saw the value of resolving forces in their x and y components. I'm going to do the exact same thing here, folks. The next step here, now that we've got our model, is I want to resolve my forces. So let's resolve forces. And I can kind of sketch them onto my model over here. I don't want to get too crazy with it, but let's resolve this one here. For example, the x component, if you look at the way that x is tending towards the negative direction on this force here, tending towards negative, the shadow, if you will, of this up here is going to go that way. So this might be our, let's just call it our 8 kilonewtons sub x. I'll call it 8 sub x for now. And then the y component is going to be tending downwards like that. So let's call this one 8 sub y for now. Let's go knock those out over here. So in this case here, my 8 sub x force would be, let's see here, again, look for triangles. So we see the triangle right here. We see that this leg would be the adjacent leg of a triangle. This is the hypotenuse, so adjacent hypotenuse cosine, right? So 8x is going to be this force here, our 8 kilonewtons times the cosine of 51.34. 8 cosine 51.34, but let's not lose sight of the fact that that's actually going in the negative direction, so we need to put a negative on that. And if I plug that in and crank that one out, folks, that's actually going to work out to be equal to minus 5 kilonewtons. Then my 8 component going down the y direction
y'all take a look at that, make sure we see this. Is that gonna be a positive, or is that gonna be a negative? How many of you are gonna go with negative? Good, all hands should be flying right now, because that's going, so if that's showing model-wise, positive Y that way, that's going down that way, it's gonna be negative, so it's gonna be -8 times, in this case, the sine of our angle, so 51.34 here. And folks, we plug that in and crank that one out, we're gonna find that ends up being -6.25 kilonewtons, and we got that one knocked out. Let's also resolve TAC. So TAC is going to have an X component going off this way. So there's TAC, we'll call this one TAC sub X. And a Y component it's tending towards negative here, so down going that way, so call that one TAC sub Y. So over here, so TAC sub X is going to be, and once again, see the triangle here, folks. Can't say this enough. So here's our triangle going down like this. We're looking for that leg right there is TAC sub X. So I got the hypotenuse, my angle, that's the adjacent, so it's going to be the hypotenuse times the cosine of 30.96. So TACX is going to be TAC cosine, whatever I just said it was, 30.96. Since I don't know what TAC is, I'm done with that. That's as far as I can go with that. TACY, and by the way, that TACX was tending towards positive X, so therefore it's a positive number. But TACY, as we all should be able to see, is tending towards negative here, so that's going to be minus again. So that's going to be equal to minus TAC times, in this case, the sine of 30.96. And then, of course, just like that, now we've got our forces resolved into our X and Y components. And what's important here, ladies and gentlemen, is this puts us in position now to solve the problem. If you think about the sequence we just did, narrative, graphic, model, from which the math comes from. We're in the middle of the math part right now. Now let's solve the problem. In this case, we just have to understand what was being asked of us. What was being asked was that we were going to figure out what TAC was going to be, such that the net effect, in other words, the total effect, was going to be a downward force here at point A. But we said going into that that also meant that there would be no force in the X direction. So if there's no force in the X direction, then what's the value of that force? 0. So if we sum up forces now in the X direction, which I think I'm going to do it way the heck over here. If we now sum forces in the X direction, what we're saying is we want that sum to be equal to 0. And from our components, our resolved forces, remember we said this, forces that are collinear merely add together. So in other words, the X forces can be added up. So I'm going to see that TAC cosine 30.96 that's one of the forces, minus this one up here, or I should say plus this, but that's a minus, so it's going to become minus, so minus 5. And again, say it over here, but I'll repeat myself, is equal to 0. One equation with one unknown. That's solvable. So now if we just do the algebra on this, we all know if we slide that -5 over to the other side, the equal sign becomes a positive 5. Turns out that TAC is going to therefore be equal to 5, I've slid that to the other side of the equal sign, divided by my cosine of 30.96. Folks, plug that in and crank that out, and you're going to find out that TAC ends up being 5.83 kilonewtons. So just like that, the first part of this problem has been answered. Remember, the problem wanted to know how much tension did we need to put in cable AC in order to cause the net effect to be nothing but a downward force. We've done that. By setting it 5.83 kilonewtons, we are assuring that the total force in the X direction is 0. The last part was simply then, okay, so what is now the resultant? The resultant of those forces, of the two cables. Now, if you think about this, the resultant becomes the single force that represents an equivalent system for these two forces right here. But if we said that the only force in this is going to be a purely downward force, then all we need to get the resultant is just sum up the y forces, right? So the resultant that we're looking for is going to be nothing but the sum of the forces in the y direction, which is going to be the following. So y direction forces here, I'm going to have negative 6.25, which we already calculated, and then minus TAC sine of 30.96, and we've already made a determination that TAC was 5.83 kilonewtons. So let's just replace that, since it's a known. And folks, if we take negative 6.25 and subtract from it even further, 5.83 times the sine of 30.96, it's going to turn out that our resultant force here ends up being equal then to minus 9.25 kilonewtons. And that solves the problem. That, folks, is fundamental equilibrium. That's all there is to it. There's not a lot to this, folks. Fundamental equilibrium is basically just utilizing the idea that in a static system, forces have to add to zero. Now, in this case here, you might say, but the resultant was not 9.25. You're 100% right. If there wasn't something holding this tower up, if we had nothing but 9.25 kilonewtons pulling down on this tower, what would happen? No, it'd go down like this, right? But that's not the case. Something's holding the tower up, happens to be the ground. Anybody want to take a wild stab at what the upward force would be here that's resisting the downward force on this, that's balancing this out? Oh, I love it. Yeah, that's the voice of common sense. Man, if it's 9.25 pushing down, it's got to be what? 9.25 pushing back up, right? It all makes sense the more you think about it. But we're all making that happen because of, again, utilizing equilibrium. And as we're starting to see here, and we're going to see it in much, much more detail as we go along, this habit of I'm going to understand the narrative, I'm going to look for the buzzwords because they're going to tell me what I need to know, and we're going to see a lot of them still to come. I'm going to use that in a graphic representation. I need to turn those words into a picture and thankful for every time it's already given to me. But from that, the model that we're going to get the math from, which is a free body diagram, and then the math takes us to the same place every time. You'll get so tired of hearing me say it, but you're going to realize as we go along, yeah, that always is the pathway every time. Any questions about this one, anybody? How we did it? Sweet. Okay. Now, let me move on just a hair here. So if there's no questions on that, now I told you at the beginning of this, we're going to move on to something very new, or actually new and very important. Let me clean up the whiteboard here. So, here's the question for us. We all know that when we apply a force to something, that force is going to tend, or try, I should say, to move an object in a direction that's going to be along the line of action of that force. So, for example, I'm going to use my cell phone. I'm going to put it to good use here. If my cell phone is sitting on the table like this, and I apply a force to the cell phone, let's go along this direction here. If I apply a force to the cell phone that's pointing straight at you, all right, then I'm going to apply that force, and no magic here, folks. The expectation will be that the phone would then move towards the direction that I'm moving it in, right? I just did not tell you anything there that I don't believe anybody didn't already know from about the time you're 4 years old. In the same sense, if I apply a force now it's going to head your way, my phone is going to translate in that direction over there. Forces cause translational motion. Unless there's something resisting it, something balancing it, the objects are going to get in motion. So here's the question for you. Right now, my phone is in equilibrium. It's not going anywhere. It's not moving. Now, if I apply force and I balance that force, all right? So let's say I apply a 2-pound force to the phone this way, but I don't balance it, we know the phone's gonna go that way, right? But if I balance it with an equal and opposite force, the phone goes nowhere. If I do the same thing like this, the phone goes nowhere, right? The question becomes, is that enough to guarantee equilibrium? In other words, is merely balancing the translational forces enough to guarantee equilibrium? I love your head shaking. No, it's not. Why? Because folks, think about this. When I applied 2 forces that were collinear to my phone down here, and they were equal and collinear, the phone went nowhere. But what happens if I do this? Now I separate exactly right up there in the corner. I'm going to separate this, and what's my phone? I'm applying the same forces. They're both x direction. If I sum up these forces in the x direction, they add up to 0. But yet my phone is doing, it rotated. So no, it turns out that forces by themselves, or summing forces translationally by themselves, are not enough to guarantee equilibrium, because forces also tend to cause, as we all just saw it right there, rotation. This gives rise, well, 2 things. Number one, that tells us that everything we've done so far as equilibrium, like we just saw in the tower problem, where all we have to do is some forces in the x direction and y direction, we are also good, everything's fine. But it's going to turn out that the sum of forces, the sum of force in x, the sum of force in y, and later on the sum of force in z, is going to turn out they're not enough. They don't guarantee equilibrium, because in any time you have forces that are not concurrent, I didn't really dwell on that, but remember the 2 forces in the tower? They both intersected at a single point. That made those forces concurrent forces. Because of the concurrency, that was enough to specify equilibrium. But just like with the phone, if we have forces that are not concurrent, they never intersect. Those forces will cause rotation, and therefore we need more than just summing forces. So basically we need to describe equilibrium as a balance of the forces that would cause translational motion, and also, when applicable, the balance of the forces that would cause rotational moment. And this gives rise to the concept of a moment. A moment, simply put, folks, is the tendency of a force to cause rotation. In fact, if you pull out 10 different books on statics and look at 10 different definitions of a moment, I promise you they'll all look slightly different, but at the end of the day, it gets really, really simple here, folks. But I want to write a version of this that I think is the salient way to think about this. So if you'll bear with me a minute, but I encourage you to make sure you get this down into your notes here. So, definition of a moment. There's a lot of stuff packed away in that definition right there, folks, and I want to make sure that we all have an understanding of what is buried within that. The moment of a force about, and notice I underlined the word any, the moment of a force about any point or axis. When I say any, so I'm talking about a mechanical system. So if I took my phone right now and I put my phone back on the tabletop over here, and I want to figure out the tendency of a force to cause rotation, I can pick any point I want. It can be a point on that phone, it can be a point where I'm standing right now, and wherever that force is applied, I would be interested in how that force might tend to cause rotation about that point. That's what's being said right here in a little bit better wording than what I just articulated there. The moment of a force about any point or axis. Now, here's an important thing for us to understand, folks. There is no such thing as a moment about any point. That's a purely modeling construct, yet everything we're going to do until the last couple of days of the course is about a point. Why? Because we're limiting ourselves to 2D statics. So when I draw something on the board, all right, if I drew a blob, let's say I've got a mechanical system here, and my mechanical system is just some black box blob, right? And I've got a force associated with this mechanical system. Let's say the force goes along that line of action right here. And let's say that I'm interested in any point. So I just arbitrarily pick a point right there. Arbitrarily pick that point. The moment of that force about any point or axis. So here's my point. In reality, x-axis goes that way, y-axis goes that way, and the z-axis in real world is that away, right? It's coming towards you. So when we see a point, what we're actually seeing is the 2D representation of the axis. Leads to something important later on in mechanics, the idea, the notion being that moments, and by extension what we better know as torques, torques are axial phenomenon. You take a motor, for example. When a motor rotates, it's rotating on an axis. If I drew the end of the motor and drew the axis as merely a point, I would see the rotation about that point. But in reality, the rotation is rotating about an axis within the motor. Same thing going on here. So the moment of a force about any point or axis, is a measure of the tendency of that force to cause a body to rotate, importantly, about that point or axis. So the moment about that point right here, due to that force, is going to be different than the moment that that force causes about this point right here, or this point right here. It's always the force with respect to the where. About what point or about what axis are we talking about? Okay, that part is profoundly important. It's important for us to know too that moments, just like forces, are vector quantities. So they have magnitude, they've got application, location, but they've also got directionality. And we've already asserted that directionality thing, but I'm going to remind you of what that is. For all moments, let me write it this way, a moment. A moment is positive if it causes counterclockwise rotation. I wrote motion, that should be rotation. About a point or an axis. And then by what should be obvious extension, and I won't rewrite all the wording, but if it causes clockwise rotation. So while here, if my moment tends, or if my force tends to cause counterclockwise rotation, we call that positive. On the other hand, if my force causes clockwise rotation, like that, we know of that as being a negative moment. So as I look at this force right here, and this is a very important point I'm about to make with y'all folks, if I look at this force right here, if the moment that I'm interested in is about that point right there, then this force right here, if again, think about this point as being like, let's say I stuck a pin in this blob, and I put a force on this this system, this blob system right here, yet it's pinned right here. That would cause the blob itself to rotate about the pin here in a clockwise sense, right? Because of that, that moment would be because it's clockwise, that moment would be negative. But check this out, the exact same force, no difference in the force whatsoever. If I contemplated the moment that this force now causes about this point right here, let's say I put a pin in that right there, I apply a force here, now my blob would rotate about this pin in a counterclockwise sense. So you see, that would be a positive moment. Same force can cause a negative moment in one case and a positive moment in the other case, same force. What's different is, again, where is the moment center, the point or axis that we're rotating about, where is it, and did it cause a clockwise versus a counterclockwise rotation? I'm emphasizing that, folks, because I'm here to tell you a mistake that's just waiting for you to make it. We will see forces from time to time. You look at this force right here and you say, okay, well, hey, you know, if my X and Y axis system was drawn like that, then I'm looking at that force, and that force is purely a X directional force, so therefore it's positive. That's going to cause a positive moment because it's a positive force. Nope. It causes a positive or a negative moment because of the direction of rotation. In the same vein, if this force was going this way, and I've seen this mistake made so many times, folks, if this force was going off this way, somebody might look at that and say, oh, that's a negative force, so my moment's going to be negative because the force is negative. Nope. In this case, this negative direction force is causing a clockwise rotation here, so negative about that point, but down here, that's causing a counterclockwise rotation, so it'd be positive about that point. It makes no difference if the force was positive or negative, none whatsoever. What did make a difference is what's the direction of rotation.
So when it gets to the positive x and y axis, it's going up, right? Like, that's kind of.
I'm not following. Help me understand that. So I think you're on something interesting, but
Okay, so if you have, I mean, when you get to like between the 3 and the 12 o'clock position,
Yeah.
and it's going up. Like
Yes.
The value is increasing as you go along there. If it's counterclockwise, it's the opposite.
yeah, that's an interesting take on that. I need to work the math out in my head, but that's an interesting take. Yeah, good stuff. Now, what have you guys noticed? Is it me or is the HVAC system in here total shit today?
Today there's supposed to be a heat stroke. There's a heat stroke warning out right now.
I'd say we should be looking for a heat stroke watch in this room right now. It seems nasty. I always thought this is kind of funny. Like we're the, we're supposed to be like one of the premier engineering schools on the planet, and it's like you'd think we'd be able to pull off the miracle of like a working HVAC system. We are currently about 106 years old, and guess what? We've never had in 106 years a working HVAC system. So, love it. Okay, so I'll tell you what. I treat that as actually good news because I'm not going to keep us here forever. This place is starting to burn alive. But having said all that, there's one thing that's missing now. One thing that remains, and that is we know that the moment is a vector quantity, directionality, where's it at? In this case, it's the where's it at part is about what point we're talking about. All that's left is the magnitude. The magnitude of a moment, folks, oh, you're going to love this one right here. The magnitude of a moment is nothing more, and I'm going to write this as m, so for all intents and purposes in this course, whenever we use the nomenclature capital M, we're going to be talking about a moment, okay? So a moment, its magnitude is nothing more than the magnitude of the force times the distance between the moment center. I'm going to use that term over and over again. The moment center is merely the specific name we give to the point of interest, the point about which the moment is being taken. So if I want to know the moment about that point, that's my moment center. If I want to know the moment about that point, that's my moment center. If I want to know the moment about that point right there, that's my moment center. The magnitude of a moment is given by the magnitude of the force multiplied by the distance between the force and its moment center, but with a caveat. The distance has to be the minimum distance, all right? So when we look at this line of action, this force right here, remember, lines of action of forces can go forever, they do go forever along that line of action. Just by the mere fact that the arrow is being drawn right there, it makes no difference. That arrow could be over here, and we're gonna get the same result. But the distance I'm looking for is the shortest distance between a moment center and the line of action, which must always be then, let me draw this one in red. That distance must always be along the line that causes a 90-degree angle with the line of action of that force. That's the minimum distance. So here's my D right there. If I want to know the moment that this force here creates about that point, I need to take the magnitude of the force, whatever it is, and multiply it by that distance right there. Moment, voila. That's it. That's literally it. You're thinking, oh my gosh, man, how can I possibly ever screw that one up? Trust me, here's how you're going to do it. The way you're going to screw it up is you're going to inadvertently think, because you're going to be given a distance, like let's say you were given the distance between here and right here, this distance right here to there. You're going to say, oh, I know my distance, it's that line right there. No, it's not. It's the shortest line. It's got to always make a 90-degree angle. And no, trust me, it's easy to get fooled into thinking it's something other than that, but it's not. Questions on that? Let's see an example. Let's see an example, and then maybe we're close enough to getting out of here. This won't take long. Simple enough, folks. I've got a bracket sitting here. The bracket, as y'all can see, is a curved bracket. Although my artwork is not demonstrating it perfectly, it's meant to be a perfect quarter circle. So I got a quarter circle bracket going up like so. I got a point A down here. I got a 250-pound force that's being applied. As you see it right there, I want to point out to you all that if we contemplated a traditional X and Y axis right here, that is a purely negative Y direction force. You might easily look at that and say, oh, it's minus 250, so it's going in the negative Y direction. But no, we're not interested in that. We want to find the moment caused by this force about point A. So what is the moment caused by this force about point A? Well, folks, this one is straightforward as it gets. If we just remember that our moment by definition, the magnitude of that moment by definition, is nothing more than force times distance. Right now, if I ask you all, what is the magnitude of that force? I don't need to see a show of hands, but I wouldn't mind having it. How many of you would tell me that the magnitude of that force is minus 250 pounds? Good. It's not. The magnitude's 250, right? The mere fact that it's pointing in the negative Y direction, who cares? The magnitude is 250. So right now I know that my value of F is 250. How about my value of D? Well, if my moment center here is going to be about point A, this is the point of interest, therefore it's the moment center. If I look at and I extend the line of action of this force forever in both directions, it goes down through here, it goes up this way like so. The distance that I need is the distance from point A over to the line of action such that that distance causes a 90-degree angle. That's what I need. And in this case right here, because we were given, and again, emphasizing this is meant to be a quarter circle, and we're given its radius, then the distance from the center here up to right there is 3 feet. the distance from the center to right there is 3 feet, and the distance from the center to right there, A, is 3 feet. So it turns out, folks, super simple here, that this is going to be our force, which is 250 pounds, times the distance, which is 3 feet. And if we plug that in and crank that out, 3 times 250 is 750. So I'm gonna get 750 units, foot-pounds here. 750 foot-pounds of moment. Am I done now? Did I specify the force? I'm sorry, did I specify the moment? Well, I specified the moment's magnitude. I know that the magnitude is 750 pounds, but a moment is a vector quantity. So I know the magnitude. I know the where is it located, in this case about point A. What about the directionality, folks? Look at this. I want you all to study this and ask yourself, I want you to think through this. Is that force causing a clockwise rotation about A, or is it causing a counterclockwise rotation about A? Get it in your mind what you think it is. It's clockwise. Now, how do I know that? Well, again, if I think about the line of action of this force going this way, and if I think about this being my anchor point, if this was a pin, and I really did push down on this curved member like this, the curved member is going to rotate this way about the pin, right? So that's going to be clockwise. That's one way to see it. If, as you looked at that, if you're like, I'm not really sure, is it clockwise, counterclockwise? Okay, key point. You got to get sure. Before too much more time, we got to very quickly be sure of this, because uncertainty about clockwise versus counterclockwise, that's going to really mess things up in no time flat. So if it doesn't resonate with you as you're looking at this and you're like, I don't really see that, there's a couple of other tricks you can use. One, remember you can slide a force anywhere you want on its line of action. So imagine you slid this force down here, right where my finger's at. If I then tied a string from this point to my arrow here and I let the arrow fly, that string is going to constrain the arrow and it's going to make it wind around A in the clockwise direction. That might help you see it. Please hear me though when I say this. After a few tries of this, if you're still having trouble, if you personally are still having trouble seeing how the rotation goes, stop and see me and just let me help you see that. So you don't want to be a week from now. You don't want to be a week from now and I'm still like, I don't see it as a clockwise, counterclockwise. You don't want to be there, folks. So now, because of the fact that this one here causes a clockwise rotation, then that means our directionality is clockwise is negative, right? So that means that when we complete this, we actually need to do one of two things. You either need to put a negative sign in here to note that that is a negative moment, or you can also do this. You can also write this as 750 foot-pounds followed by the letters CW. CW meaning clockwise. CCW, of course, meaning counterclockwise. That is a way to do it. In fact, in the book, and the answers in the back of the book, you'll see that they use the CW, CCW notation all the time. So make sure y'all understand what that is. But CW, negative, whatever, it's going to cause, we need to see that as clockwise versus counterclockwise. Anybody have any questions on that one right there? How we just did that? I'm going to show you one more, then we're going to be out of here. But this sets up a really important conversation on Thursday, and I mean really important. So let's check this out. Let's imagine that we've got a simple circular drum. And I'm just going to show the end of the drum. So the end of my circular drum looks like a circle. And let's say the center of that circle is right there. And let's say that I've got a force that's sitting up here at the very top of this. In fact, let's do this. Let's let our y-axis go right through there. So there's our y-axis. Here's our x-axis like so. Let's say that I've got a force sitting up here that is 100 pounds. Going in that direction right there, 100 pounds, and let's say that that is making a 30-degree angle with respect to the y-axis. And in this case here, let's call our center down here, the center of the circle. Let's call that point O for the center. In this case here, I want to find the moment, and I'm going to shorten this up here, folks. Find the moment about point O. And when I say find the moment, of course, I'm obviously talking about the moment caused by that force right there. So, all right. In the there's nothing new here department, we already know that the magnitude of the moment is equal to the force times the distance. In this case, magnitude of that force, folks, magnitude of that force is 100, obviously, right? So we got the F part down, no problem. Distance, different animal. In this case here, now, what's the distance? Oh, I forgot to add one thing. Let's put, let's let the radius of this drum, be 12 inches. So the radius of the drum is going to be 12 inches. So, if my force is equal to 100 pounds, if I use 12 inches for my distance, am I right or wrong? And everybody says, wrong. Why? Because we already remember that the distance we're looking for is if I extend my line of action forever this way, my line of action forever that way, I'm looking for the distance between my moment center and my line of action of my force that causes a 90-degree angle right there. But no problem in this particular case right here, because in this case here, if I want this distance, I'm going to call this one D, that's what I'm looking for, there's my D. We've already started being conditioned to, for everything we do in this course, we're always looking for triangles. In this case here, if this is a 30-degree angle right here, then according to geometry, that's also a 30-degree angle right there. I see a right triangle here that involves that leg, which I know is the same as my radius, so 12. I got a 30-degree angle, D, which is opposite that 30-degree angle, and this leg of the triangle here is my hypotenuse, so opposite hypotenuse sine. So according to this, the sine of 30 would be equal to the opposite leg, so it's going to be equal to D divided by the hypotenuse 12, or D is therefore equal to 12 times the sine of 30, and the sine of 30 is 1/2, or 0.5, therefore D is equal to 6 times 0.5, which is 6 inches, and folks, with that very simple step forward, now we're in a position to come over here and say, all right, moment, this is going to be equal then to the magnitude of my force, so 100 pounds, times my distance, which we just calculated to be 6 inches. And if I plug that in and crank that out, I'm going to get 600. The units on this are going to be inch pounds. And I'm not done, though, until I specify, is this causing a clockwise or a counterclockwise rotation about this point right here? Is this force here going to cause counterclockwise rotation or clockwise rotation? Counter. Everybody needs to see that. And if you don't see it, slide the force down. Imagine there's a pin through here and put a force on this that's going to cause the wheel to rotate in a counterclockwise sense, or tie a string to the arrow, whatever it is. So because that is counterclockwise, that makes this a positive force, or a positive moment. Therefore, you could end this off by maybe just writing CCW, or a plus behind it would be perfectly, or in front of it would be perfectly fine too. So two really fast ways of getting moments. They both relied on ultra simple step, force times distance. When we get together again on Thursday, I'm going to work a problem for you that's going to look something like what I'm just going to sketch here ultra fast. I'm going to work a problem in which we're going to contemplate force applied to an end of a basketball hoop. And we're going to want to figure out what is the moment that force causes about a point right there and about a point right here. Here's what I want you to plant in your minds. If I had to figure out, by extending this force down here, what the distance is from this point to here, I probably don't have enough information in the problem to do that. As you're going to see, it's enough of a total pain in the butt with the information that's going to be given in this problem just to figure out the trigonometry, to figure the distance from here down to the line of action of that force. That means that while the first couple of examples we just saw here for calculating moments were easy and straightforward, we're going to move away from easy and straightforward to something nasty really fast. So the question becomes, what can we put in the toolbox that'll take a problem like this and make that doable without spending until our next birthday waiting for the trigonometry to work itself out? The answer is, there is something remarkably important called Brignon's theorem. And I'm going to give you the highlights of Brignon's theorem. Varignon's theorem simply says, if I have a force and I want to know the moment that that force creates about any point, then if I can create an equivalent system to that force, an equivalent force system, then the moment caused by the equivalent force system must be the same as the moment caused by the original force system. And why is that true? Because remember, equivalent systems have the same effect on mechanical systems. So what we're about to find out is this. If I take this force up here, and once again, if I create an equivalent system by resolving it into its components, if I resolve this into its y component, and I resolve this into its x component, and I know that when I do that, I get rid of the original force, but now I got this force and this force. If I want to figure out the moment about this point right here, is it not true that the line of action of this force goes right through that moment center? If that's the case, then what's the value of D? 0. This force doesn't even come into play. But this force here, that force has a finite distance from the moment center. That force right there, by the way, would actually have been our 100 times the sine of 30, so that would be 50 pounds right here. That 50 pounds has a moment arm given by the original dimension of 12. 50 times 12 is 600. Didn't we get 600 over there? That's Varignon's theorem in 30 seconds. We're going to formalize that. We're going to see how we're going to use that to make a problem like this go from impossible to quite doable. We'll do that on Thursday. Questions, anybody? Good. Let's get out of here.